All right, so making a video for Bree in California. Oh well. Any questions on the review? How'd it go? Hmm? Went okay. We'll give it a shot here. Let's see if I can turn this into a whiteboard. There we go. Now I've got just a clear whiteboard we can play on. Okay. Did all these multiple choices come out perfect, or do you have some questions?
7 and 9.
7 and 9. Let's take a look.
And 12.
Okay, number 7 says, a certain spring elongates 9 millimeters when it's suspended vertically and a block with a mass M is hung on it. The natural frequency of the mass spring system is what? Okay. Two ways to deal with frequency. We could say omega is the square root of k over m, yeah? That's called the angular frequency. Or the regular frequency is 1 over 2 pi square root of k over m, which is actually the equation for the period is on your equation sheet. Here's the period, 2 pi square root of m over k, yeah? So if we take the period equation and flip it, you got the frequency equation. Now, here's the problem. They didn't give us k, and they told us mass m. They didn't give us the mass. So here they don't give us the mass, they don't give us the k, so how do we solve it? If you take a spring and you attach a mass and it stretches a certain amount, in this case like 9 millimeters, so 0.009 meters, how would you find the k? Don't worry that you've got some variables missing. What would you do to find k? Yeah. F equals negative kx. Now, if the force is external, the force and the x are in the same direction. So if you want to drop the negative sign and just say that k is F over x, you'll be okay. Now, the force is mg, right? And the x is 0.009. So you say, well, you know, if I put in my numbers, I know g and I know 0.009, but I don't know m. But look what happens when I stick it into the frequency equation. 1 over 2 pi square root of mg over 0.009 divided by m. So you go, wah. And I do know what g is, and I do know what x is, and I do know what 2 pi is, so I can figure it out. So sometimes just have some faith in the person who wrote the problem that, I don't know that particular variable, but maybe if I keep going, just keep moving forward, something will cancel out. So that's kind of what's going on in number 7. So go ahead and finish punching it out, and hopefully you get the right answer. You said 7 and 8, or 7?
9.
Sir?
I said 9.
You said 9, excuse me.
You wanted 16.
You wanted 16?
16, 8.
Oh, okay. So let's just keep going. Number 8 is 0.2 kilogram mass attached to a spring whose spring constant is 500 newtons per meter, executes simple harmonic motion with an amplitude of 0.1000. Its maximum speed is. All right. Come on. There we go. So in number 8, we know the mass. We know the K. And there we go. Much better. And we know the amplitude. V, the velocity at any time, negative x sub m omega sine of omega t plus phi. Okay, what's the maximum velocity then? If that's the velocity at any time, maximum velocity is what? X sub m omega. Because when this guy equals 1 or negative 1, we've reached a maximum or minimum for v. So there's our maximum. X sub m, hey, they gave it to us. Omega, that's the square root of k over m. Look, they gave us k and m. So we're set. Number 9. A 0.25 kilogram block oscillates on the end of a spring with a spring constant of 200 newtons per meter. If the oscillation is started by elongating the spring 0.15 meters and giving the block a speed of 3 meters per second, what's the amplitude of oscillation? Okay, so what's going on here? This is a little weird. You have to kind of visualize what they're doing. So I'm going to use my oscillator up here. Let's get the stormtrooper out of the way. What they're saying is, okay, we're going to elongate the spring 0.15 meters, so 15 centimeters over that way. And we're going to give it a velocity of 3 meters per second. So we're going to elongate it, then we're going to do. So at this point, it's got two things going for it. It's got an elongation of 0.15, and at that point, it's going to have a velocity of 3 meters per second. And we'd like to know what's the amplitude of oscillation going to be. So we start it here, and we give it a push. What's the amplitude going to be? Now, there's two ways I can approach this. I could use the velocity, position, acceleration, force model, or I could use energy. Because this is number 9 for those who are listening, right? Because I know the total energy of the oscillator equals its potential plus its kinetic. What's the equation for total energy of an oscillator? Sir?
It's just the potential energy equation.
Potential energy at one end, right?
Yeah.
Okay? It's that simple. When it's on the ends, that's how much potential energy it's got. Its potential energy at some other point would be 1/2 kx squared. Its kinetic energy at some point would be 1/2 mv squared. So the question is, do we have enough info to solve for that? Can we come up with the amplitude? Let's see if they gave it to us. Oh my gosh, they told us the mass is 0.25 kilograms. They told us the spring constant is 200 newtons per meter. They tell us x at a particular moment is 0.15 meters. Whoa, that's a 5. And they told us the velocity at that particular point is 3 meters per second. I think we're cooking with gas, folks. They gave us so much information, we're overflowing. So, y out the 1/2, solve for x sub m, because we know k, x, and v, and m. All right, so that'd be the approach I would take. Not the only approach, but I think that's the simplest one. Okay, that's 7, 8, 9. There was another one out there somewhere. Amanda, you had a different one. 6. Acceleration of a body executing simple harmonic motion. Oh, this is a weird question. Okay. Thank you for asking it. This, yeah, number 6. All right. Acceleration. The equation for acceleration is what? Omega squared, yes. And then all this blah, blah, blah stuff back here. And then the velocity is negative x sub m omega, sine of omega t plus v. So what's going on here is that the acceleration is a negative cosine function. So a cosine function usually starts here and does its thing. So we have to start it here and have it do its thing. Okay, now the velocity function, if I graph it on the same graph, which is kind of weird, but I'm going to do it anyway. The velocity is a negative sine function, which now a normal sine function starts at 0 and does this. A negative sine function does this. Okay, I've got to get this right now. I want to peak it there and cross and peak it right here. No, I want to peak it right there. Ah, Mr. Ebele, you're losing it. Okay, that's really terrible. But here's the point. If you look at this wave, the black wavy line, that represents acceleration. You look at the blue wavy line, that represents the velocity function. So the question is, how far apart are they? Angularly, how far apart are they? I know from here to here, that's 2 pi, right? So it's like this guy is occurring at pi, and this guy is occurring at like 3/4 or 3 pi over 2. So the difference between them is pi over 2. The answer is 90 degrees. If you've got a sine function and a cosine function, they're absolutely identical. If you just take one of them and shift it over 90 degrees, you've got the other one. So it's kind of a weird question. It's the way the question's worded is kind of strange. The acceleration leads the velocity by, okay, the acceleration peaks 90 degrees or pi over 2 radians before the velocity peaks. Okay. Next.
Whoa.
Ooh. 12 is kind of a mean one. I couldn't do this on a multiple choice on the test. I can do it a multiple choice on the review, but not on the test, unfortunately. I'd have to make this a problem. Now, a physical pendulum, being a meter stick, there's the center of mass, and let's say here's the pivot. And they're saying the distance between the center of mass and the pivot is A. And we actually did this problem, or a similar problem, in one of the problem sets. We said, okay, the period of a pendulum like this is 2 pi square root of I over mgh. Remember, we're looking at the I about this point right here. About the center, I is 1/12 ml squared. About the pivot, I have to use a little ditty known as the what class?
Parallel axis.
Parallel axis theorem, which says that 1/12 ml squared plus ma squared, the distance from the center of mass to my pivot, A, that's going to be my new rotational inertia. So here's my T. T is 2 pi square root of 1/12 ml squared plus ma squared all over mga. They keep changing the variable h to something else. In the problem we did, it was d. Now it's a, and when we derived it, it was h. So it's like, make up your mind, idiots. Okay, so we would like to find the a that minimizes the period. So if you've got a function you want to minimize, what do you got to do to it?
Take the derivative.
Take the derivative and then
Set equal to 0.
set equals 0. You remember doing this one?
Yeah.
We did this one in class, yeah. So what we would do, now, again, street calc, right? I could minimize this whole thing, or I could say t is minimized when the insides are minimized. So I could say, I'm just going to minimize this stuff in here and say, okay, I've got this function of A, function of A that says, oh, and by the way, mass cancels out.
And
Wow.
L is just 1, right? So you don't have to deal with that either.
Oh, that's true too. Just call it 1/12. Hey, that's very wise. Especially being a multiple choice, you don't care showing your work, right?
Exactly.
Just let L equal 1 and lose it. And so take the derivative of that, set it equal to 0, solve, and then choose the answer that's closest. Now, if this actually were to occur on a multiple choice question on the AP exam, you know what I would do? You got a okay, that's one possibility, skip it. But you got a calculator. Put in A equals 0.1 meters. Check the answer. And then do a second entry. And change the 0.1 to a 0.2. Then change the 0.2 to a 0.3. Just check a few. You'll find the shortest one really quick. It'd be a lot quicker than doing all this stuff, right? So in multiple choice, you don't have to show your work. It sounds like cheating, but it's not. It's a multiple choice question. So if they give you a bunch of answers, say which one's the best, you go, okay, I'll just check a few of them out. So that might be the better choice. The wisest choice is probably to skip it and come back later, because this will take 15 minutes. You can do 15 problems in 15 minutes, 15 questions. So you could get this 1 point, or you could get 15 other points elsewhere. All right. So number 12, I couldn't do that on the test to you. I mean, I could do it as a problem, but I couldn't do it as a multiple choice problem. Anything else? Sure?
Will there be a problem with parallel axis?
Yes, you should know the parallel. Yeah, definitely. Thank you. In fact, I came up with a problem last night just to re-emphasize that. Yeah. Definitely be able to use the parallel axis theorem, especially in the context of a physical pendulum. Good question to ask. Everyone, mail him $5. Makes a lot more sense when there's 30 people in the classroom. I always say, when someone asks a question like that, and then they get an answer, basically telling them what's going to be on the test, I say, okay, all 30 of you, put $5 in an envelope, send it to Lucas. All right. How you doing?
Is that sound your projector?
Mm-hmm. It's really laboring lately. That bulb's overheating. And I cleaned the filter too, so it's not lack of air, it's just the bulb is ready to pop. I understand they really make a loud noise. I don't remember one ever going though. I know they've replaced it once, but they'll probably pop when I'm gone for some reason, and the sub will be here and they'll be watching a movie. Blammo! She can let them out in groups of 10 to go change their undies.
I've got a totally unrelated story if you want to hear it.
Well, please hang on to it, though. I do want to hear it. Anything else from the textbook or the multiple choice? It doesn't have to be multiple choice. It could be textbook, too. All right. I'd like you to try one for me. We didn't quite get there last hour, but, you know. All right, it says quiz at the top, but we're just going to do this together. If you want to think of it as a quiz, go for it. It says a disc with a mass of 1 kilogram and a radius of 0.4 meters is attached to a 2-meter string. And then the string is, it's hung from the ceiling. I didn't write all that out because I got a picture there. If the combination is swung with a low amplitude, what is the period of oscillation? So last year you would have looked at this and said, oh, I'm going to treat it like a point mass. It's a simple pendulum. This year you're going to say, oh, I can do better than that. Now I'm smarter. I know more. Which is actually two different things. I prove that every day. I'm not smart, I just know a lot. Much finer flakes than last night. I can still see the grass though. Would have been embarrassing to have a snow day today. I know, Caledonia, Dutton, those were the only two I saw. That was at 6 o'clock this morning though.
My neighborhood is super ice now.
Yeah.
What's the inertia of the
Sir?
disc? What's the inertia of the disc?
Oh, yeah. A disc. I pulled this out of my pocket. Okay. Let's see. I hate it when that happens. Oh, okay. I know what I have to do. I hit this, and then I hit this. There we go. All right. So I for a disc about its center is 1/2 mr squared. And yes, I would give that to you on the test. I won't make you derive those. How's it going, my students? Getting there? What'd you get, Doc? Let me look over your shoulder then. I'm just kind of curious. Ooh, I got something a little bigger. Oh, okay. Now, check it out. You need parallel axis theorems over here. Because this is the eye about here, about this point. What you need is the eye about that point.
Is it 3.1?
So this is about the center of mass, call it the CM. So the I for the pendulum is going to be ICM plus MH squared. Remember, H is from here to here. It's from the center of mass to the new pivot point.
So you said 3.1?
Yep. That's what I got, 3.1 seconds. you cooking, Jake? Sure. You're so enthusiastic.
You say the answer is 3.1. I got 2.9.
Okay, we'll check it out here.
I think I just rounded wrong.
You divide from the radius by 2, d squared.
No?
Where'd the 1/2 come from on the h squared?
Oh, you're right. Thank you. Lose that, baby.
Maybe it's because I solved for I first. That's the number I got.
What'd you use for H?
I think 2.1.
Use
Why
one,
did I use
2.1?
2.1?
2.1.
So I thought you were going to say 2 because a lot of people just use the length of the string. But we want to go from the center of mass of the disk all the way up to the pivot, so we need 2.4 there.
I made the radius 2 point, or 0.1 instead of 0.4. That would be,
Oh, that would do it.
that would be where it
That's the only error you made. All right. Turns out the mass of the disk, you don't need it, do you?
Why do they do it?
I don't know.
I used it to solve for I.
That's for proportional. It's when it like spins this way.
Oh, I see. All right.
So that actually came out to an even number, it was like 4 or 0.449. So nice number.
This way.
So I don't know how I got my radius from.
All right. So I got 3.1 hertz. Oh, I'm sorry. That's 3.1 seconds. Duh. Mr. Everly, some days doesn't pay to get out of bed. There we go. 3.1 seconds. All right. So that's actually a really simple problem. The part that gets folks, though, when they encounter one of these is that parallel axis theorem every time. Okay, so I can say it until I'm blue in the face, but until you run into it yourself, you don't believe me. You need the parallel axis theorem when you're dealing with a physical pendulum. Because oftentimes you know the I about the center of mass. What you need is the I about the pivot point. All right? You cool now with that? Because I knew people would make that mistake. That's why I wanted to do a practice problem.
Is T equals 2 pi squared I over mgh? Is that on the equation sheet?
It is not.
Which ones are on
You have a copy of the equation sheet. And if you've lost it, it's on the Moodle page. Let's see. For this particular unit, let's see. Looks like they've got x equals x sub m times the cosine of omega t plus phi. So just like our book, they use a cosine for that oscillator. They've got t equals 2 pi over omega equals 1 over f. They've got t for a simple harmonic oscillator is 2 pi square root of m over k. They've got t for a simple pendulum is 2 pi square root of L over G. What else? They have force of a spring equals minus kx. They have potential energy of a spring is 1/2 kx squared. Another one we used in this chapter, 1/2 mv squared. That, of course, is on there. Okay.
I don't think we ever got copies of these versions.
Okay, well then go to my Moodle page and print it out. So, yep, you do have an electronic copy in your possession. So just, yeah, check it out. Make sure that that all is good. There's all kinds of amazing things on my Moodle page. All right. So yeah, there it is. AP Physics C equation sheet right off the bat.
I just always get
By the way, there's two nice links. The Physics Classroom and Hyperphysics are really good. I can take those off. Then, when you pop down here, review, let's see, here's the chapter 15 solutions. So all the solutions to all the problems we've done this chapter. So that's kind of a nice thing to go through is, you know, what if Mr. Evely had trouble coming up with a new problem, so he just took an old problem and changed the numbers? You'd be all set. Then we've got the review solutions here. So the review from the book. So I haven't received a lot of questions today about the book, so I'm assuming some of you haven't looked at it yet. Is that possible? Haven't looked at the book problems yet? Jake, look at the book problems yet on the review? Yes. No. Well, you still have tonight to work on it. But remember, my solutions are there. And if something doesn't make sense, make sure you give me a call. Actually, we have a robotics meeting tonight, but it's over at 5. So I should be pretty available tonight to answer questions and stuff. So there's all kinds of cool stuff here. Here, there's all the examples we did in class. Did we do this problem together on Friday? We did.
Yeah.
I was sitting there last night going through my lesson plans thinking, I don't remember doing this second hour. So make sure you can do, how's that? Put up $5 in my envelope. Make sure you can do this problem here, or ones like it, because I really, number one, I really love ballistic pendulum problems, and number two, ballistic pendulum type problems, or ballistic oscillator problems, whatever you want to call them, they do tend to show up. So remember that bullet block collision is completely inelastic. And you know what that means? Conservation of energy, at least for the collision part, conservation of energy is useless. You can still use conservation of energy on the other parts of the problem, but for the collision, no conservation of energy. All right. Now, one thing we didn't cover in the chapter, but we did cover it last year. In the other class, I have 2 students who didn't take honors physics. The last section of the chapter is resonance. And you remember all about resonance from last year? Resonance is that idea that everything has a natural frequency, a frequency at which it loves to oscillate. And so if you've got a natural frequency at which you love to oscillate, the best way to oscillate you is at that frequency. It's getting kind of personal, isn't it? So let's see. That is not what I wanted to do. Let's try this. Oh, check this out. There we go. All right. So okay. So when you attempt to drive an oscillator at its natural frequency, it results in maximum transfer of energy from the driver to the oscillator. And here's the equation from your book. Driving frequency, this is angular frequency, but it doesn't matter. Driving frequency equals oscillator frequency, you have resonance. And the simplest example I came up with, and this is actually in your book too, is when you're pushing a little kid on a swing. When you push a little kid on a swing, he's a pendulum. He's not a simple pendulum, but he's pretty close. And when you apply your force to him, you want to do it at a specific frequency. And it turns out to be the same frequency at which he is oscillating. So you apply your force every time he goes through one full swing. So if your frequency matches his frequency, you get maximum transfer of energy from you to your oscillator, little brother. If you hit him at a frequency that's not equal to his natural frequency, then you get a mess. You slow him down, you reduce his amplitude, you knock him off the swing, he runs to mom, you get in trouble. Okay. Notice also, I didn't talk about this last hour because it's really probably not on the test, but notice that my frequency, if you take a look, I lag behind his just a little bit. In other words, to get the maximum transfer, I don't push him right when he's here. I push him when he's just a little bit starting to, so it's like if you looked at my sine wave and his sine wave, they'd be just a little bit off. So the driver lags behind the oscillator just a little bit, and you get maximum transfer of energy. It's kind of like, you know, because I don't want to push him right when he stopped. I want to push him when he's just ready to get going again. So there's that little tiny bit of phase difference between the oscillator and the driver, which makes things a little bit easier. And two examples. One is the coupled pendulum back here. So I've got two pendulums with precisely the same length. And what determines the frequency of a pendulum? Two things in this world. It determines the frequency of a simple pendulum. G and its length. So experiencing the same G, probably. Same length, as best as I can do. And you saw this last year. It's still amazing. Because they're connected, this guy becomes the driver of this guy. And since they have the same natural frequency, you get maximum transfer of energy from one to the other. Then he stops, and he becomes the oscillator, and he's the driver. But he's driving this one until he gives up all his energy. And now this guy becomes the driver of this one. And there's just no end to the joy. Well, there is. It'll eventually stop. Got to ask the honors physics question. Will it go on forever, Mr. Evelyn? Yes. I should just say that sometime. Mr. Evelyn, will that go on forever? Yes. The tough one is making it go in a circle. So if he goes in a circle, see, it immediately goes elliptical. And I notice total transfer occurs in one dimension more than another dimension. So now he's circular, and then he goes straight, and then eventually loses that. So it's like it gives up its motion in one dimension before it gives up. That's just freaky. I don't know why. And then, of course, the standard, everybody does this demonstration. You've got two tuning forks with the same natural frequency, and you drive one with the other. So, in some ways, this is like the coupled pendulum too, because they transferring energy back and forth, back and forth, back and forth. It's hard to hear over that stupid fan in the greenhouse. I'm just gonna unplug that thing and let all the plants freeze. Live up to my name. All right. So that was a little section that we didn't cover in class, but whoa! That picture fell off the wall. Oh, ended up in the recycling. I can't lose this. It's a picture of me and the robotics team beaming out. It's so awesome. Alrighty. Anything else I can help you with? We've got until 49, so that's like 10 minutes, 9 minutes from now. Y'all good? All the ones from the book went well? Up till now? You still have tonight to work on, but you haven't started them all, huh? McGraw. What were you doing all weekend?
Well, Saturday I was pretty busy. Friday night I did homework, but I didn't have physics.
Ah.
And Sunday I really worked. I did homework at night and I still did.
Yeah. Helps when you get an A in the class, too, I suppose.
Yeah.
Dang it. I got to lower your grade so you pay more attention. All
I
right.
normally do the problems that I put it
Yeah. All right. Get through them. There are some that are less vital than others. I was going through them last night, and there was one that just... Which one was it? No, that wasn't it. Yeah, number 16. Lose that one.
Which one?
Number 16. It's a good problem. It's worthwhile doing, but it's just, I think it's more trouble than it's worth, actually. The rest of them are pretty good. I was running through them last night, just checking to see what my practice quiz ought to be. All right, so use the remainder of the time to work on some problems. And I need to conference with a couple of students here. So first thing I'm going to do is turn this off.